All right, just a tiny little review of some of the gas law information besides just plugging and chugging numbers in and solving those equations. First off, here we see a cylinder, a container, and there's a movable piston, and you can see that from the first cylinder to the second, the piston has moved downwards. And inside, we have a gas. And what we notice is that when the piston smashes the gas down, the particles get closer together. So they're farther apart here, closer together here. Remember, pressure is caused by particle collisions. More collisions, more pressure. So just like we talked about during rush hour, when the highway has more cars, there's more likely to be an accident, a collision, when there's more cars on the highway. So when we smash a gas down, when we decrease the volume that the gas is in, pressure goes up. And this is what Boyle's law was talking about. And so you could be asked questions about relating pressure and volume, and that is how you would want to answer. This is the one law where as the volume goes down, pressure goes up, inverse relationship. And this is the law that had this picture problem associated with it. So in this first cylinder, in this amount of space, we had a pressure of 150 kilopascals. When the volume is cut in half, the pressure will double. So it goes up to 300 kilopascals. When the volume is doubled, when there's an expansion of the volume, more room for the particles, that's going to cut the original pressure in half. So that's how we get the pressures as far as those pictures are concerned. The number of particles, again, we're just taking a peek in, and if there's 1, 2, 3, 4, 5, 6 particles here causing 150 kilopascals of pressure, if the pressures double, if they're smashed, when we take a peek in there, we're going to see twice as many. We're going to see 12 of those particles. All right, so you can just draw one and say 12. That's acceptable. On the flip side, when the volume is double and there's more room and we take a peek in, we're only going to see half as many as the original. We're only going to see 3 of those particles. So again, that picture problem goes along with Boyle's law, and hopefully you can answer that successfully. Here we see a rigid container with a gas in it, and when it is heated up, the particles inside move faster, more chaotically, there's more collisions. And when there's more collisions, my pressure is going to go up. So again, we have a rigid container. It doesn't have the capability of expanding and contracting. This is like when we were talking about with the popcorn. A popcorn kernel is a rigid container. You heat it up, the water inside turns to gas, pressure builds and builds and builds until boom, it can't take anymore. And this is courtesy of Gay-Lussac's law. All right, so that's the pressure-temperature relationship. As temperature goes up, pressure goes up. And again, this is when the volume of the container is held constant, along with the amount of gas. Here we see the hot air balloon. Now, when I heat up the gas inside the balloon is able to expand. When I cool the gas inside the balloon, it is able to contract. So now our volume is changing with temperature, and that is courtesy of Charles's law. Again, Gay-Lussac's law, the volume is constant. It's a rigid container. Charles's law, the volume is allowed to change because we have a flexible container. Here we see 3 balloons, and they all appear to be the same size, so they have the same volume. 3 different gases, though: hydrogen, oxygen, carbon dioxide. They're at the same temperature and same pressure. Let's call that STP. And so what we say is 1 mole of any gas at STP will have the same volume, the magical number of 22.4 liters. And this is courtesy of Mr. Avogadro, because we know that 1 mole of a gas will have 6.02 times 10 to the 23rd particles. Same number of particles, same number of collisions, same pressure, same volume, lots of good sameness. Last one here, the law that we talked about when we were mixing gases together is Dalton's law. And so this was our other picture page. And so we have gas A in a container, gas B in a container, and then we mix them together. Gas A has a pressure of 200 kilopascals, and that's courtesy of 1, 2, 3, 4, 5, 6 particles. Gas B only has 3 particles. Half as many particles, half as many collisions, half as much pressure. Then we know when we mix gases together, the total pressure of the mixture is the sum of the partial pressures. So my mixture has 300 kilopascals of pressure. I hope this helps as you are preparing for your test, and
I hope that you end up having a very good score on your test. Ha 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 ha. See you later.